Section 14.2 Bronsted-Lowry acids and bases. In 1923, J.N. Bronsted in Denmark and T.M. Lowry in Great Britain expanded the definition of acids and bases to include bases that do not contain hydroxide ions. A Bronsted-Lowry acid can donate a hydrogen ion to another substance, and a Bronsted-Lowry base can accept a hydrogen ion. A Bronsted-Lowry acid is a substance that donates a proton, and a Bronsted-Lowry is a substance that base is a substance that accepts a proton. A free hydrogen ion, which is a proton, does not actually exist in water. Its attraction to polar water molecules is so strong that the hydrogen bonds to a water molecule to form a hydronium ion, H3O positive 1. We can write the formation of a hydrochloric acid solution as a transfer of proton from hydrogen chloride to water. By accepting a proton in the reaction, water is acting as a base according to the Bronsted-Lowry concept. Hydrogen chloride plus water yields hydronium ion plus chloride ion. In another reaction, ammonia reacts with water. Because the nitrogen atom of ammonia has a stronger attraction for a proton, water acts as an acid by donating a proton. The water donates a proton to ammonia, making it ammonium, and leaving water as a hydroxide ion. Conjugate acid-base pairs. According to the Bronsted-Lowry theory, a conjugate acid-base pair consists of molecules or ions related by the loss of one proton by an acid and the gain of one proton by a base. Every acid-base reaction contains two conjugate acid-base pairs because a proton is transferred in both the forward and reverse directions. When an acid such as hydrofluoric acid loses one proton, the conjugate base fluoride ion is formed. When the base water gains a proton, its conjugate acid, hydronium, is formed. Because the overall reaction of hydrogen fluoride or hydrofluoric acid is reversible, the conjugate acid of hydronium can donate a proton to the conjugate base fluoride ion and reform the acid hydrofluoric acid and the base water. Using the relationship of loss and gain of one proton, we can now identify the conjugate acid-base pairs as hydrofluoric acid is the conjugate acid, fluoride is the conjugate base, hydronium is the conjugate acid, water is the conjugate base. Table 14.4 gives some more examples of the conjugate acid-base pairs. In another reaction, ammonia accepts a proton from water to form the conjugate acid ammonium and the conjugate base hydroxide. Each of these conjugate acid-base pairs, ammonium is the conjugate acid, ammonia is the conjugate base, water is the conjugate acid, hydroxide is the conjugate base, is related by the loss and gain of one proton. Ammonia NH3 acts as a base when it gains one proton to form its conjugate acid, ammonium. Water acts as an acid by losing one proton to form its conjugate base, hydroxide. In these two examples, we see that water can act as an acid when it donates a proton or a base when it accepts a proton. Substances that can act both as acids and base are called amphoteric or amphiprotic. For water, the most common amphoteric substances, the acids or bases behavior depends on the other reactant. Water donates a proton when it reacts with a stronger base, and it accepts a proton when it reacts with a stronger acid. Another example of an amphoteric substance is bicarbonate. With a base, bicarbonate acts as an acid and donates one proton to give carbonate. However, when bicarbonate reacts with an acid, it acts as a base and accepts one proton to form dihydrogen carbonate. Amphoteric substances act as both acids and bases.